So we are on live, we can start.
Okay.
Yeah.
So hello everybody. So welcome to the first live session of the course Computational Complexity. Right. So this is the first time I'm teaching an NPTEL course and also first a live session of that course. If you have any questions or feedback or comments on how you're how you're finding the course material, general suggestions, anything, you're welcome to post these comments in the YouTube comment box. There was also a Google form that was floated, and I saw only one question in the Google form responses. So yeah. So how many of you, I would like to know how many of you are there watching? So I'm myself watching it, and it says 2 watching. So is it correct to assume that only one more person is watching this? So okay, now there are more people watching. Yeah. Yeah, so I'll just briefly talk about the course, and then you could go to we could discuss specific questions, right? So very briefly, the course is about computational complexity, right? And and it's about computational problems, like even simple things like adding, multiplication, sorting numbers, searching for something, computing the shortest distance in a graph, right? So when you want to, or computing the common GCD of 2 numbers, or multiplying 2 matrices. These are all computational tasks, right? Factoring a number, or taking the square root of a number. These are all computational tasks. And some of these are easier than some others, right? So what makes some of them, like for instance, multiplication seems to be harder than addition, right? If you have similar sized numbers, it's easier to add them than multiply them. So why is the case that some of them are easy and some of them are not easy, right? So this is the whole point of this course, is to understand why this is the case, right? So we will be categorizing computational problems into what are called as complexity classes. And complexity classes basically divide the computational problems into groups. Like that's why they or classes. That's why they're called complexity classes. So on what basis? On the basis of how much resources they take, right? So the commonly used resources are time and space. And during the course, we will see other resources, like for instance, the randomness, how many random bits we use, or how much interaction we perform, or we will see other models of computation which are not Turing machine based models. So in those models, there will be some other parameters that we will look at, right? And we will try to attempt to understand how these classes relate with each other. Like, is it that this class is a subclass of the other class? Is it that this class is contained inside the other class? Is it that there is some intersection, but then otherwise there is nothing common about it? Many things, right? So these are the kind of things that we will try to do. So it's an extremely interesting course, and very interesting techniques that are used to make all these inferences, right? And as I mentioned it in one of the lectures, I think lecture 3 or 4, most of this course, what we will see in the course, was developed in an attempt to answer the P versus NP question, right? So what is P versus NP? P versus NP is the class of all computational problems that can be decided in polynomial time, deterministic polynomial time. NP is a class of all problems that can be decided in non-deterministic polynomial time. Or NP is a class of all problems that can be verifiable in polynomial time, right? So, right. So I'm seeing that comments are coming in. So I'll get to the comments very soon, the YouTube comments. Yeah. In the meantime, please keep them coming, and we'll discuss about the specific questions that you have. Right. So if I give you a graph and I want you to check that it has whether it is colorable using 3 colors, it is not easy to do that. It's not efficient. It is not easy to do that in an efficient manner, right? Because there are, let's say you want to check it's colorable using 3 colors. There are n vertices. Suppose there are n vertices in the graph. There are 3 power n possible colorings. 3 power n possible 3 colorings, and some of them will be proper. Some of them may be proper. Some of them may not be proper. And if there is very less number of proper colorings, it's hard to search through the space. Or just because the space is so huge, there are 3 power n possible colorings. However, it is easy to verify a coloring whether it is proper. I give you a graph with a coloring assignment. It is easy to verify, right? So this is the difference between P and NP. NP just requires verification, right? And P requires you to come up with the answer as well. So seems that verification is easier than coming up with the answer, right? It is easier to it is easier to appreciate a musical symphony than creating it, right? So the P versus NP question is asking, is it the same, right? Is it the same to create something? Is it the same as appreciating the same thing, right? That's what the P versus NP question is asking in a kind of very, very high level. So P equal to NP, the answer is yes. If they are the same. If P is not equal to NP, they are not the same, right? So if P not equal to NP means, so the answer is widely believed to be P is not equal to NP. However, the question, as I mentioned in one of the videos, has been stated and been there for 50 years. Perhaps around 10-15 more years if you account for the time that it was there in people's minds but didn't get explicitly stated. Correct. Now let me get to the questions that you have asked. So course is extremely useful. Thank you for the comment. Is it possible to share the annotated notes? Of course, I want to do that. Just that, as I mentioned in the beginning, it's the first time I'm teaching an NPTEL course. So many of these things, I'm like how to make it available to you, I hadn't figured out. So very soon I will share it with you. Very soon I will share the material with you. And there are also, so there is this Google Groups where you can ask questions. And I'm also, based on some suggestions, I was also thinking of creating a Discord server for interaction between students. I noticed that the Google Groups is not very crowded, like very less number of people. Actual number of registrants are actually part of the Google Groups. So I thought I will also advertise the Discord server. So all these announcements will be coming to you very soon. Some of these I didn't know how to convey, so that's why it took some time. So yeah, any other specific questions? Okay, please start Discord. Yeah, of course. Yeah, that's what I just said. There is there are some questions. I think only one question that came to me. I think. So that's about, and yeah, that's only one question. So the question was, when you want to show that a language is NP complete, where do you reduce it from, right? So to show that language is NP complete, you need to, or one of the ways of showing that language is NP complete is to one, show that language is an NP. This is the easier part. usually. And two, we need to show that all the languages in NP are reducible to this, right? And this, usually we don't reduce all the languages in NP to this. What we do is we reduce an already known NP complete language to this language. So the question is, how do you decide which language to pick to reduce from, right? So this is not really it's not really, there is no strict formula or this thing. So you tend to look for similar problems, right? So like if you, I think this is in the week 2 material about when we show that SAT is NP complete first, and then we'll show that 3 SAT is NP complete. So SAT and 3 SAT are similar problems. So one would assume that you could reduce one to another, right? For instance, clique and independent set, there is some similarity. Clique is asking for whether there's a set of vertices such that all of them are adjacent to each other. And independent set is asking whether there's a set of vertices such that none of them are adjacent to each other. So you can see there is some similarity between these two problems, right? So the idea is to be able to reduce one to the other. So you should be able to, so when you want to reduce A to B, or when you try to reduce A to B, you want to, the reduction process, one is that the reduction process should be in polynomial time, right? It should not take too much time for the reduction itself to happen. And two is that every yes instance should be mapped to a yes instance, and every no instance should be mapped to a no instance, right? So and it's not so this tends to be easier if the problems that you choose are similar, right? So okay, so there is a question, how this similarity is being decided, why identifying the problem. So there is no, as I said, there is no clear recipe for this. Similarity is not a formal measure or anything that I said. It's something that you tend to identify, like some patterns. This looks like that, or this particular problem seems to behave in some ways like the other problem, and we know that this problem is NP complete. So we could reduce this to that, or we can attempt to reduce, right? So whether the reduction actually happens itself is not very clear. It depends. So many of these things, these proofs are not, they're not easy to come by the first time this happened, right? Many of the NP completeness proofs, people still take up problems and show that these problems are NP complete. So it's not like coming up with an NP completeness proof is very, very easy. But some of the problems are not that difficult, right? Especially when the problems are very, very similar. We have done some reductions in the course, maybe in the second week of the lectures that will come up, right? So as I said, there is no clear recipe for finding the similarity. It's just if you play around with a lot of problems and you see a lot of languages, you'll understand. You start getting a feel for this. Yeah, there are books where there are lists and lists of NP complete problems, right? So many NP complete problems listed, right? Any other questions? Any logistical questions or any suggestions about the space of the lectures? Do you find it easy? Do you find it too easy? Do you find it difficult? These kind of answers, these kind of feedback will be most helpful. I suppose there is some feedback mode that NPTEL gives you, but if you want to share now, it'll be nice to hear. Okay, there is another question. Yeah, so in fact, most questions are from the same person. It'll be nice if more people ask questions. The question is this difficult sometime to show that a problem is an NP? So usually it is the easier part to show that a problem is an NP, right? Because what you have to do is To show that a problem is an NP, all that you have to do is there is a non-deterministic polynomial time algorithm, right? Again, NP stands for non-deterministic polynomial time, right? And not polynomial time. Usually, so like in the case of three coloring, the way to show that it is an NP is to show that you can verify that a coloring is proper. Verify that it's a three coloring and that it is proper. And this is not that difficult to do. To show that a graph has a Hamiltonian path, for instance, it's one gives a Hamiltonian path, and all that one has to do is to verify that it is a Hamiltonian path. Right? So what is it that you have to verify? You have to verify that there is a sequence of vertices given. First, you have to verify this is an entire all the n vertices are there, and there is no repeats. There are no repeats, and that there is an edge between vertex 1 to vertex 2, vertex 2 to vertex 3, and so on. Like all the vertices are getting covered, and that is a valid path. So usually, to show that something is an NP is fairly straightforward in most cases. There may be some specific problems where this may not be that easy, but we will not get into these type of problems in the course. Any other questions? Any other suggestions? Is this possible to not keep a lecture session of not more than 10 minutes and annotated slides? So annotated slides, meaning the notes that I'm preparing, I have already said that I will share it with you. To keep a lecture session for not more than 10 minutes, that may not be that may not be the easiest thing to do, but I will try to see how to organize things, because there are some proofs that we'll see in the course that are best presented at a stretch rather than breaking it up. So, or even if I'm breaking it up, I have to break it up at a certain logically appropriate places. So it is not like, but if I let's say, if 40-minute proof, if I break it into 4 pieces, it may, I feel it will be worse to follow than easier. Is there a specific reason for requesting 10-minute sessions? Is it a technical challenge, or is it if it's a technical challenge, then I understand the difficulty. But if it's if you think for understanding, from my side, from the understanding perspective, I will try to do whatever is best for the understanding perspective. Yeah, so the question, there's a comment, 40 minutes is too long. So is it too long from what perspective? From a technical perspective or an understanding perspective? Conceptual perspective? Again, I don't try to intentionally make it 40 minutes. What happens is that if I try to restrict it to 30 minutes, sometimes the content becomes too cramped, or some explanation has to be skipped. So yeah, I'll try to keep this in mind, how to break it down better. Any other points? Any other specific questions? Sure. Yeah. So I get the suggestion. I'll keep this in mind. Any other points? So how one question. So how many? So there are 7 people watching. I think one of which is myself. And, uh, so out of the people who are here, how do you like? It will be nice to get some feedback on the speed of the lectures. Is it too fast or too slow? Or you're fine with the pace as it is now? Um, uh, any other specific suggestions that any of you may have? And yeah, there are no further questions. If there are no further questions, I think, what do I say? Just 1 second. If there are no further questions, then we could close the session. The whole point was to understand how the course is being handled, mainly because I am covering, I am teaching an NPTEL course or any course through the online medium in an asynchronous way for the first time. I have taught online courses in a synchronous setting, but not in this asynchronous where I just record lectures and then release it, right? So textbook except SIPSR. So is there any other textbook except SIPSR? So I will share whatever material that I'm preparing, that I'm using during the class. For now, whatever content we are seeing, SIPSR is perfect. And I myself have just followed. There are other books which are there which I've listed in the Swayam portal. I think one is Papadimitrio's book, one is Arora and Barak's book. These are the other 2 books, but till now we have not really reached that place yet. Gary and Johnson, yeah, I myself I don't have a recollection of how Gary and Johnson was. I haven't learned myself from Gary and Johnson. So, but if you find it good, you can follow that as well. The standard material will be good everywhere, wherever you look. Any other questions? If you have no other questions, and I'm also not really. I think I also have asked whatever I wanted to ask. If there are no other questions, I'll be happy to close the session. Again, feel free to use the Google groups, but we'll also soon share the Discord. We have already, so the reason is that I want to do it after, like I was just figuring out how to release the information to you, because the Google groups, I found that it is not very populated. So once I get, I'll soon share the materials also. Yeah. Okay. Okay, then. So till the next session, where we'll have the live interaction, keep watching the videos and keep posting questions, and through Google groups or Discord or whatever means. Yeah. And yeah, happy learning. Okay. If you have any suggestions, anything, you can always send it through these forums. Right. Maybe I'll just wait for 1 more minute and then close the meeting. Okay, then I think we'll close it. Thanks again. Yeah, bye.